Among the finds from Kalahoyuk in central Anatolia is a lump of corroded metal about 3 centimeters across. If the dating holds, it is the oldest iron-making debris ever recovered anywhere on Earth. Someone left it there between the 20th and 18th centuries BC, nearly 1,000 years before iron became common anywhere in the region. The people who produced it had no thermometer, no notion of chemical elements, no concept of oxidation, and had never once watched iron run as a liquid. They made iron anyway. That scrap is the direct ancestor of the 1,849 million tons of steel the world poured in 2025. It is the ancestor of the beam over your head, the frame around your screen, and the blade in your kitchen drawer. The obvious question is who invented iron, and it is the wrong question. The answer that changes how you see the nail in your wall lies somewhere else. Pure iron melts at 1,538 degrees Celsius, and nothing these people could build came close. The real question is how metal was pulled out of stone when nobody could make that metal flow. The answer was never a hotter fire. It was a colder one. Bronze hit a problem that had nothing to do with metallurgy. The alloy required 2 ores, and the 2 are almost never found in the same ground. Every bronze workshop in the region sat at the end of a supply line hundreds of kilometers long. The metallurgy itself had been solved centuries earlier. Copper melts at 1,084 degrees Celsius, a temperature a well-built pottery kiln already reached, and the alloy poured cleanly into molds. The map could not be solved. A war or a change of dynasty in a distant valley could stop the tin, and when the tin stopped, the axes stopped. Iron sat outside that entire system, and it was not an alternative to bronze. In the Bronze Age, it was not a working material, and treating it as one distorts everything. Merchants at Kultepe-Kanesh in central Anatolia kept records of iron changing hands at up to 40 times the value of silver by weight. Silver was money. Iron was rarer than money. Jacqueline Waldbaum once assembled every scrap of Bronze Age iron reported across the Mediterranean and parts of the Near East. The total came to roughly 150 objects, most of them from the 4 centuries before 1200 BC. That is 150 objects across half a continent and 2,000 years. None of that inventory was a tool for doing work. Iron turns up as studs on an ivory box at Asamhoyuk, set beside gold and lapis lazuli, and as blades laid in tombs. Even the sources of that metal were not what they appeared to be. The iron beads buried at Gerzeh in Egypt around 3400 BC were shown to be meteoritic. The dagger blade from the tomb of Tutankhamun, buried in the 14th century BC, gave the same answer. The most precious metal in the ancient world was falling out of the sky, so the ceiling held. Fields were cleared, forests were cut, and ships were built with a metal that depended on 2 rare ores meeting on a trade route. The rock that could have lifted that ceiling was lying in the ground beneath almost every settlement in the region, and it stayed there. Iron makes up about 5% of the Earth's crust by mass. It is the 4th most abundant element there, behind oxygen, silicon, and aluminium. It is also the 2nd most abundant metal on the planet. Tin, the other half of bronze, is scarce enough that its deposits dictated trade routes across a continent. The 2 materials were never competing on equal ground. One had to be carried, the other was underfoot. Iron reaches the surface in ores that are neither hidden nor exotic. Hematite, magnetite, limonite, and siderite outcrop on hillsides, wash out in riverbeds, and darken beaches as heavy black sand. The eastern shore of the Black Sea is known for exactly that kind of iron-rich sand. People in these regions were not merely living near the ore, they were handling it. Ground hematite is red pigment, and it had been ground for that purpose long before anyone considered it a source of metal. At Kalahoyuk, excavators recovered a possible piece of ore from the Hittite period. The likeliest reading is that the mineral served as pigment rather than as furnace charge. The closest thing to a solution anyone had was being used to make things red. Copper ores advertise themselves. Malachite is green, azurite is a deep blue, and both surrender beads of metal when they sit in a hot enough fire packed with charcoal. Iron ore advertises nothing at all. A lump of hematite in an ordinary hearth stays a lump of hematite and comes out looking much like what went in. There is no bead, no shine, no moment of transformation for anyone to notice and repeat. The obstacle was never access to the ore. The obstacle was that the ore gave no signal that anything was inside it. There was one exception, and it was the least reliable supply line in the ancient world. Metallic iron does occur naturally on Earth without any smelting at all, and geologists call it telluric iron. Deposits are extremely rare. Nearly all of them are very small, and the only population known to have worked them systematically were the Inuit of Greenland. Everywhere else, iron already in metallic form had arrived as a meteorite. Researchers can usually tell the two sources apart. Meteoritic metal tends to carry nickel in the range of 6 to 20%, alongside a nickel to cobalt ratio near 18 to 1. Some pieces also show a banded internal structure of kamacite and taenite under a microscope. Forging at high temperature can erase that banding, which is one reason the arguments about who smelted what have run for decades. Early iron objects from Anatolia often contain nickel, but usually below 3%, which points away from the sky and towards a furnace. That is the analytical signature of the whole transition, and it is faint. The written record is no louder. Hittite scribes used a phrase that translates as iron straight from the furnace, which suggests that at least some of their words for iron meant smelted metal. Yet the most quoted iron document of the Bronze Age is a complaint. In the 13th century BC, the Hittite king Hattusili III wrote to an Assyrian king about an order of iron. The store of good iron at Kizzuwatna had run out. This was not a suitable time to produce more, and the work was unfinished. He sent a single blade point in the meantime. That was the industry. This is the fact worth stopping on. The fourth most abundant element in the crust reached one of the great powers of the age as a gift from the sky and an unfilled backorder. The obstacle was not the ore, and it was not effort or organization. It was a number. The number is 1,538. Pure iron turns liquid at 1,538 degrees Celsius, and below that mark it does nothing a metalworker would recognize as useful. Copper becomes liquid at 1,084 degrees. The two metals therefore sit 453 degrees apart, and that figure is the reason the Iron Age arrived so long after the Bronze Age. Every metal these societies had already mastered sat below the copper line. Lead runs at about 327 degrees, silver at about 962, and gold at about 1,064. A charcoal fire under a steady blast of air will reach all three of those temperatures, which is one reason those metals were worked first. Iron stands alone above the line. The distance is not a question of a few more logs and a stronger arm. Temperature in a furnace does not only decide what melts, it also decides which oxides will surrender their oxygen and which will not. Every metal oxide has a threshold below which it holds on to that oxygen, no matter how long the fire is kept burning. Manganese oxide will not release its oxygen until the furnace passes roughly 1,400 degrees, which is already beyond anything these people could build. Silica holds on until about 1,600. Alumina never yields at all, and even a modern blast furnace leaves it sitting in the slag. None of these limits can be negotiated with by working harder or waiting longer. They are thresholds, and a furnace either crosses them or it does not. A smelter working below a threshold can repeat the same procedure for 1,000 years and receive the same nothing every time. The second half of the barrier had nothing to do with heat. Smelting, as these societies understood it, was a visual event. The proof that the operation had worked was a bright liquid gathering at the bottom of the hearth, and that liquid was also the product. Pour it into a mold, let it cool, and the work is finished. With iron, no such proof can appear at any temperature a Bronze Age furnace is able to hold. The metal, if it forms at all, forms as a dull gray mass wedged among cinders. It looks like the residue of a failed operation rather than the reward for a successful one. Anyone reaching into that hearth would be sorting through what any experienced worker would call waste. So the barrier stood in two parts, and both were absolute. The temperature at which iron behaves like the metals they knew was 453 degrees above the highest melting point in their working experience. The only signal that would tell them a smelt had succeeded could never appear at all. Crossing that barrier demanded something that existed in no workshop anywhere in the world. It demanded a way of taking metal out of rock without ever melting the metal. The chain of improvements that ended in iron was built by people trying to make copper. Nothing in that chain was aimed at the metal it eventually produced. The first change was height. A copper furnace can work as a bowl or a low shaft, and over generations those walls were raised. Experimental reconstructions of these furnaces show what the extra height actually does to the interior. In a furnace charged with charcoal to 80 centimeters, instruments have recorded two separate environments inside one structure. The upper zone held between 800 and 1000 degrees, while the lower zone ran past 1200. When the same furnace was charged only to 50 centimeters, that division collapsed, and the whole interior sat near the higher figure. The taller stack was not hotter, it was layered. That layering turns out to be the whole difference, and nobody raising those walls was looking for it. The second change was air. A clay pipe through the wall, fed by a bellows, let an operator drive oxygen into the burning charcoal at a chosen point. In one modern reconstruction, the bellows delivered gusts of roughly 5 seconds each, hour after hour, for the length of the smelt. Forced air raises temperature, and it also decides where in the stack the fuel burns hardest. The third change was preparation. Ore was crushed to fragments roughly a centimeter across and roasted in an open fire before it ever went into the furnace. Crushing exposes surface, and roasting drives off water while converting one iron mineral into another. Both steps make a rock more willing to react, and both spread because they made copper smelting more reliable. Not one of these changes was an attempt to smelt iron. The people behind them were solving a different problem, and they were solving it well. Copper ores are rarely pure copper minerals, and slags from copper production can contain dendrites of iron oxide and, in some cases, particles of metallic iron. That is the accident in its simplest and most widely discussed form. In strongly reducing conditions at the base of a copper furnace, iron can leave the charge as solid metal without anyone intending it. Thomas Wertheim proposed in 1973 that the earliest smelted iron was exactly this, a byproduct nobody ordered. The idea is tempting, and it remains unproven, and metallographic work by Merkel and Barrett in 2000 argued directly against one version of it. A separate reading holds that the first furnaces yielded only tiny fragments of metal that had to be forged together before they amounted to anything. What a furnace of this kind produces, then and now, is not an ingot. It is a porous, spongy lump of metal shot through with trapped slag, and metallurgists call it a bloom. The furnace that produces it has been called a bloomery ever since. No document records who lifted the first one out of the ashes. This reconstruction rests on excavated furnaces, on slag chemistry, and on repeated modern smelts, not on anyone's account of a discovery. The archaeological record preserves the process in great detail and loses the person completely. One question is left, and everything that follows depends on the answer. Why does the metal appear at all? Start with what comes out, because that is all anyone in the ancient world could judge. A charge of crushed, roasted rock is fed in at the top, a few handfuls at a time, over the course of several hours. In modern reconstructions, 30 to 40 kilograms of good ore will yield a single coherent lump weighing 8 to 10 kilograms. The lump is far heavier than it looks, holds together under a hammer, and can be forged into a bar. At no point during those hours does anything inside that furnace come close to 1,538 degrees, the temperature at which iron turns liquid. The metal never becomes liquid, and it never needed to. The reason is that iron in the ore is not metal at all. It is iron locked to oxygen, and the entire problem is the oxygen. Breaking that bond has its own threshold, and the threshold sits far below the melting point. Wootz, the last oxide in the chain before metal, releases its iron at a minimum of 720 degrees under the right conditions. That is 808 degrees below the point where iron would run. The reaction is sluggish there and only proceeds at a useful speed above 900 degrees. Even 900 leaves an enormous margin. Metal appears in the solid state, grain by grain, inside a piece of rock that keeps its shape throughout. Metallurgists call this solid-state reduction, or the direct process, and it is the exact opposite of casting. If you have ever watched molten metal poured into a mold, you have watched the other kind. Here the iron never flows anywhere. Nothing pours, nothing is skimmed, and there is no moment when a shining surface appears. The particles form exactly where the ore particles were, then sinter together at their points of contact into a rigid metallic scaffold. That scaffold, gathered and hammered while still hot, is the bloom. The furnace does not work by burning, it works by starving. An operator who lets too much air through gets heat and no metal, and every experienced smelter has to fight that instinct. In one long-running experimental program, the tap holes drilled below the air pipe had to be plugged again immediately after each tapping, specifically to stop carbon monoxide escaping. That detail contains the whole chemistry in miniature. The valuable thing inside the furnace is not the fire, it is a gas. In front of the air pipe, charcoal burns to carbon dioxide and releases an enormous amount of heat into the surrounding stack. The hot carbon dioxide then rises through a column packed with glowing carbon, and what happens next is the reason the process works at all. Above about 1,000 degrees, carbon dioxide meeting hot carbon converts back into two molecules of carbon monoxide. Chemists call this the boudoir reaction, and in a bloomery it runs continuously, regenerating the reducing gas as fast as the ore consumes it. Carbon monoxide, not carbon, strips the oxygen from the ore, which is why the process is described as indirect reduction. The gas has to be present in strength. For wootz to release its iron, at least 60% of the gas mixture around it must be carbon monoxide rather than carbon dioxide. Below that ratio, the reaction stalls, and it stalls no matter how much fuel is added or how hot the furnace becomes. The smelter has no way of measuring any of this. The gas ratio cannot be seen, smelled, or judged by color. There is no instrument, no theory of gases, no concept of a molecule. What exists instead is a set of habits, each one tuned by failure, that holds an invisible gas ratio inside a narrow band for hours at a time. Every one of those habits is a proxy for a number nobody could see. Something in the furnace does become liquid, and this is where the confusion of the ancient world was total. Molten material runs down through the stack and is tapped out through holes below the air pipe. It glows, it flows, it pools, and it is not iron. The rock around the iron oxide is mostly silica, and silica combines with iron oxide to form a compound that melts far below either metal. That compound is fayalite, an iron silicate, and it is the main constituent of the slag every bloomery produces. The slag bath in a working furnace does not much exceed 1200 degrees. Iron needs 1538. Those two numbers, and the several hundred degrees between them, are the entire reason a bloomery can exist. So the slag turns liquid and drains away through the tap holes, while the iron particles stay solid and weld to one another. This is the moment worth holding still for. The bright liquid that every metalworker of the age would have read as the finished product was, in this furnace, the waste. The gray, crumbling mass that looked like waste was the product. Success and failure had swapped appearances. The margin is narrow. Slag has to stay fluid enough for iron particles to move through it and meet. Experimental work puts the working limit near 5,000 millipascal seconds at 1200 degrees, which is roughly the consistency of honey. Thicker than honey, and the iron grains never find each other, and the smelt ends as a sticky, useless mass. In one measured furnace, about 35% of the descending charge bypassed the reducing zone entirely and ended in the slag. The list of conditions that must hold is long, and not one item on it announces itself. The metal hides, the waste shines, everything looks wrong. Two ores can enter the same furnace, under the same blast, and behave completely differently. In one experimental series, a rich ore produced steel with a carbon content near 0.5% on every single run, regardless of the air rate. A second ore, treated identically, produced blooms with almost no carbon at all. The difference lay in the rock rather than in the skill of the smelter. Carbon enters iron only at the places where bare metal is in direct contact with burning charcoal. If slag covers the metal surface, no carbon crosses. When it does cross, the metal changes category entirely. Iron with dissolved carbon is steel, and metallurgists call the process carburization. Dissolved carbon also lowers the melting point of the metal, and it lowers it steeply. At about 4.4% carbon, iron melts at 1,154 degrees, nearly 400 degrees below the pure metal. A bloom is therefore never one material. It is a mixture of fractions with sharply different carbon contents, formed in different places inside the same lump at the same time. This is where the story turns strange, The people running these furnaces could produce steel, and the archaeological record shows they produced it repeatedly. They knew which ore to choose, which fuel ratio to run, when the slag looked right, and when to break open the arch. They read the color of the slag, the sound of the blast, and the weight of what came out. They knew how to do it. They had no idea why it worked. Not one of the variables that actually governed the outcome was visible to anyone standing at that furnace. Every one of those signs was a shadow cast by chemistry that nobody would describe for millennia. Carbon would not be identified as an element until the 18th century. A process this particular, balanced between a gas ratio, a viscosity, and a narrow temperature window, ought to have been found once, in one place, and nowhere else. The furnace that spread across the Near East and Europe solved the air problem with muscle. It was a shaft of clay, sand, and straw, commonly reconstructed at around a meter in height. A ceramic pipe was set through the wall near the base. Someone works a bellows at that pipe for the whole length of the smelt, while someone else keeps the charges of ore and charcoal coming. The design hands the operator direct control of the single most important variable in the furnace. Air can be increased, reduced, or cut off, and the reducing zone shifts in response. It also ties every kilogram of iron produced to a pair of arms working for hours without a break. The yields were correspondingly modest. A single smelt of this kind is a day of work for at least 2 people. The arithmetic is unforgiving. Extractive iron metallurgy in this region, on a limited scale, goes back to somewhere in the early 2nd millennium BC. Iron artifacts do not appear with any regularity in the archaeological record until after 1200 BC. Close to 1,000 years separate the first smelted iron from anything resembling an iron economy. The reason for that gap is still argued over. One reading holds that the earliest furnaces yielded only small fragments of metal. Those fragments had to be forged together before they amounted to a usable piece. A technology that delivers a handful of grams in a working day is not something a society can be built around. The bellows made the process controllable. It did not make it abundant. Everything about this version of the furnace is shaped by the cost of the air. That cost is paid in human labor, hour after hour, for every single smelt. South of the Sahara, a different answer took hold, and it removed the bellows entirely. A natural draft furnace is built tall so that hot gas rising inside the shaft pulls fresh air in at the bottom without anybody pumping. The taller the stack, the stronger that pull becomes. A furnace built high enough will draw air on its own all day, provided the fuel column stays open. Nobody has to stand there. Several large openings are set around the base instead of one narrow pipe, because the draft is gentle and any restriction chokes it. Furnaces of this kind recorded in the Nsukka region of southeastern Nigeria measure between 0.85 and 1.25 meters across at the base. That is roughly 3 times the internal diameter of the small European shafts. The difference is not decoration. A weak draft spread over a wide hearth does the work that a narrow forced blast does in a smaller volume. The trade is straightforward once it is stated. A forced draft furnace is small, quick, and labor-hungry. A natural draft furnace is large, slow, and almost unattended, which matters enormously where people are scarce and wood is not. David Killick has argued that inventions of this kind were common in the region, and that what low population densities ruled out was not invention, but mass production. Regional variation runs deep inside the tradition as well. Furnaces recorded among the Mafa of the Mandara Mountains in Cameroon used a single vertical tuyere, whose length changed over the course of the smelt. At Taruga, in central Nigeria, furnaces and iron objects have been dated to the 6th to 3rd centuries BC on current readings. None of these builders had a bellows, a piston, or a person on the handles. All of them made iron. In southern India and Sri Lanka, the problem was attacked from the far end by sealing the metal away from the furnace altogether. Iron and a carbon source were packed into a small clay crucible. The crucible was closed, and the closed crucible went into the charcoal. Whatever happened inside was invisible, even to the person running the fire. There is no slag to read, no color to judge, and no way to look. Studies of the process indicate that temperatures above 1,400 degrees were reached within those crucibles. That is well beyond anything a bloomery hearth sustains. At that heat the charge melts, and molten iron dissolves carbon evenly rather than in patches. Sealing the charge also keeps the metal away from the furnace atmosphere, so the carbon content depends on what was packed inside rather than on the draft. The result is a cake of steel carrying between 1.0 and 2.0% carbon throughout, several times the concentration of an ordinary bloom. That material is wootz, and ingots of it traveled west for centuries to be forged into blades. Crucible fragments and metal particles from sites in Tamil Nadu push the practice back towards the middle of the first millennium BC. The air came from the weather. Excavated furnaces in Sri Lanka were sited and shaped to face the monsoon, and wind-driven examples dating from the 3rd century BC onward reached above 1200 degrees with no mechanical blast. Even the finishing step ran on chemistry nobody could name. Wootz ingots are brittle when they come out, and heating them to between 1100 and 1200 degrees strips carbon from the outer skin. That leaves a hard interior wrapped in a softer, more forgiving shell. Smiths knew the step had to be done. The reason it worked was a diffusion gradient they had no way to describe. China went in the opposite direction from everyone else and made the iron melt. Feeding a furnace with an excess of fuel drives so much carbon into the metal that its melting point collapses. Iron carrying enough carbon becomes liquid at around 1150 degrees. That is nearly 400 degrees lower than the pure metal, and squarely inside what a well-built furnace can hold. Instead of a spongy lump to be hammered, the furnace delivers liquid metal that can be poured straight into molds. The trade-off arrives immediately. Nothing about this route is easier, and it demands a taller furnace, more fuel, and a far heavier blast. Cast iron objects appear in Shanxi by the 8th century BC. Blast furnaces in China have been dated as early as the 3rd century BC, and they were oriented towards scale from the beginning. A furnace of that design is almost impossible to run below roughly half a ton of iron per day, and its efficiency climbs as output rises. A bloomery can be run by a family in a field, and a blast furnace cannot. Iron in China arrived as an industry rather than as a craft. Everything downstream followed from that one decision. The scale that made it cheap also made it visible to a treasury. Salt and iron production came under central monopoly around 117 BC. Cast iron is hard and brittle, so a second process was needed to burn the excess carbon back out and return the metal to something forgeable. Chinese workshops were doing exactly that from the 3rd century BC. European ironmaking did not adopt the equivalent step until the end of the 18th century, roughly 2,000 years later. Not one of these traditions was copying another. The forced draft shaft, the tall natural draft stack, the sealed crucible in the monsoon wind, and the liquid iron blast furnace are 4 different machines built on 4 different labor economies. Air arrived by muscle, by convection, and by season. Scale ranged from a few grams to half a ton a day. What every one of them produced was the same narrow set of conditions inside a hot column. Every one of these traditions had to satisfy the same 3 requirements, or fail. Carbon monoxide had to make up the majority of the gas around the ore. The ore had to sit in that gas above 720 degrees and stay there long enough to react. The waste had to melt while the metal did not, or in the Chinese case, the metal had to be loaded with carbon until it melted as well. The window is narrow. Those requirements are not cultural. They are set by the ore and by the gas, and they are identical in Anatolia, in Nigeria, in Tamil Nadu, and in Henan. The chemistry did not negotiate. Convergence on the same reaction does not require contact between the people who converged. It requires only that they were all working with the same planet. None of them could have stated a single one of those requirements out loud. Not one had a word for the gas, a name for the element, or any theory of why the process worked. What spread was not an idea. What spread was a set of practices that happened to hold an invisible reaction inside its window, and the world those practices built was already changing shape around the people who ran them. Every kilogram of iron made before the industrial age was a stack of cut wood. The furnace eats charcoal, and charcoal eats forest. The ratios involved are not gentle in any of the recorded cases. In a reconstruction in Rwanda, 228 kilograms of charcoal processed 40 kilograms of ore, and a reconstruction of Mafa smelting in Cameroon used 82.3 kilograms for 18 kilograms. Those are the efficient cases. At the other end of the range, natural draft furnaces recorded in Malawi consumed between 1,000 and 1,450 kilograms of charcoal. That fuel worked through 55 to 75 kilograms of low-grade lateritic ore, a ratio close to 20-1, and the ore is not the product. Only a fraction of what enters a furnace leaves it as metal. The fuel cost for each kilogram of finished iron is higher again. Charcoal also has to be made before it can be burned, and tending a charcoal pit takes days of continuous work. Set all of that against what a landscape can supply. Estimates for woodland of the kind these industries used put the maximum sustainable yield near 4,000 kilograms of fuel wood per hectare per year. Annual charcoal demand for a single production area, reconstructed from ethnographic records, ranges from a few hundred kilograms to more than 11,000. A busy smelting district consumes the annual growth of several hectares, every year without pause. Iron does not follow the ore, it follows the trees. Smelting sites cluster where the fuel is. The ore is carried to them rather than the other way round. And when the wood near a site runs thin, the industry moves or contracts. The geography of early ironmaking is a map of woodland, drawn by people reading the supply of charcoal rather than the supply of rock. A smelt fails in minutes rather than hours. In one experimental campaign, everything ran steadily for an hour and a half, and then cooling slag sealed the air pipe from the inside. Deprived of blast, the furnace began losing temperature immediately. Nothing about the failure was dramatic. A furnace that loses its air does not explode or collapse. It simply stops being a furnace. The team pulled the bloom at 160 minutes, rather than risk it cooling in place and welding itself to the furnace wall. 500 grams of ore came out unreacted. Other failures arrive from the opposite direction. Runs loaded with too much charcoal have produced slag so viscous that it blocked the shaft outright, and a full charge in that condition yields a kilogram or two of small lumps. Poor ore fails before it starts. Below roughly half iron content, the slag thickens past the point where metal particles can find one another. That threshold is a property of the rock rather than a matter of skill. What such a failure costs is worth stating precisely. A failed smelt is not a wasted afternoon. It is the days two people spent working the bellows in shifts. It is the weeks somebody spent felling and charring the wood. It is the ore that was dug, carried, and crushed by hand before any of it began. Recovering anything at all means breaking open the clay arch by hand beside a slag bath sitting near 1200 degrees. This is the point where the story changes shape. The capability that lifted the ceiling on the ancient world arrived attached to a permanent tax on forest and labor, paid in advance, every time, with no guarantee of a return. Even the size of that tax is harder to pin down than it sounds. The standard account of Roman smelting on Elba has the island stripped of trees by the 1st century BC, and a recent model of its fuel wood supply concluded that total clearance in that period is unlikely. The consequences are real. The measurements behind them are thinner than the confidence with which they are usually repeated. 3 claims about this story are repeated far more often than the evidence supports. The first is that the Hittites held a monopoly on iron and that it made them militarily dominant. Specialists rejected that reading decades ago, and the document usually cited as proof says close to the opposite. A state controlling a strategic material does not write to a neighboring king to explain that the storehouse is empty. What the evidence supports is Hittite involvement in production, possibly more than their southern neighbors managed, and nothing beyond that. The second claim is that iron replaced bronze because iron is harder. Early smelted iron is often softer than tin bronze. The hardness that made steel worth having came later and unevenly, and it depended on conditions no smelter could hold steady. Hardness requires consistent carburization and quenching, and there is little evidence that either was routine during the first surge of iron adoption. Many early iron objects copy the shapes of bronze ones, which is not what a material revolution tends to look like. The third claim is that a collapse in the tin trade forced the switch. Shortage models of that kind have not held up. Current scholarship reads the expansion of iron as a consequence of the political and economic rearrangement at the end of the Bronze Age rather than its cause. Certainty here is expensive. The uncertainties run deeper than the myths. The record is thin. Much of what gets repeated as settled was assembled from a handful of finds. For decades, hundreds of sites in ancient Colchis, on the eastern Black Sea, were described as the earliest iron-smelting landscape in the world. A program of resurvey and reanalysis showed conclusively that they are copper smelting sites. Hundreds of sites changed metal on the strength of chemistry rather than new excavation. Two of the strongest candidates for 13th century iron production in the Levant, at Tel Yinnam and Kamid el Lawz, have both been refuted. The very early dates from Termit in Niger are shadowed by the old wood problem, because charcoal can be centuries older than the fire that consumed it. Dates from arid regions carry that risk in an especially sharp form. Whether iron smelting was invented independently south of the Sahara is still an open question. And the oldest physical trace of iron production anywhere remains that corroded lump 3 centimeters wide. Nobody can say from the published evidence whether it came from smelting ore or from working metal that had already been made. That is the foundation the whole story stands on. It holds. It is also very small. Look around the room you are sitting in and find the nearest piece of metal. It will not take long. The hinge on the door, the screws in the chair beneath you, the frame inside the wall, the blade in the drawer. Every one of those objects around you exists because of a reaction that nobody could see. Steel holds up the floor you are standing on. Steel carries the water into the building and the power along the street. Steel runs through the roads as reinforcement and along them as rail. Steel turns inside the motor of every machine in the building. Steel cut the timber, poured the concrete, and lifted the beams into place. The screen you are reading this on was assembled by steel tools, shipped in a steel hull, and delivered on steel wheels. None of it announces where it came from, and none of it needs to, because the material has become so ordinary that it is invisible again. In 2025, the world produced 1,849 million tons of it. All of it descends from a process that once yielded 8 kilograms after a full day of work. The connection is not a figure of speech. A modern blast furnace runs the same reaction the bloomery ran. The furnace is taller, the blast is hotter, and the instruments are exact. But the reaction inside that column is the one a clay shaft performed 3,000 years ago. Carbon monoxide strips oxygen from iron oxide, silica leaves as slag, and carbon dissolves into metal. The equations have not changed since someone in Anatolia pulled a gray lump out of the ashes. What changed is scale, control, and the fact that the chemistry now has names. That is the whole distance between then and now. The reaction was never invented. It was found. It had been available in every hearth on Earth for as long as there had been hearths. It needed a fire starved of air, a stack of the right height, and a rock nobody had any reason to burn. Nobody set out to find it. The person who first pulled a bloom out of a furnace was trying to make copper, or trying to rescue a smelt that had gone wrong, or doing something nobody has managed to reconstruct. That person left no name, no account, and no explanation. They could not have given one. Whoever they were solving a problem that had nothing to do with the thing they found, and they went back to work the following morning. The knowledge they had was a set of habits that worked for reasons entirely outside their reach. Everything around you is standing on those habits. The floor under your feet, the frame in the wall, the blade in the drawer, the rails under the city. All of it comes from a lump of gray metal that looked like waste, lifted out of the ashes by someone who never knew what they had done.